Today we're going to take a look at solving exponential equations. We have solved exponential equations when we got a common base and we solve, but a lot of times we cannot get a common base. So what we have to do is use logarithmic inverses in order to eliminate the base. Now this is a nice little step because a lot of you are probably going to use this step even when you can find a common base. I know a lot of times I find myself doing the same thing. So take a look at this, make sure you're focusing. We only have about 4 examples we're going to go through here. We're going to do a good bit of algebra stuff. It's a new look, but a lot of it's some old stuff as well. Just 4 examples, let's be focused and see what happens. All right, really the only notes we're going to take is this little section that we have here. You don't even really need to write this down. What you need to understand is the premise of what we're doing. So the premise of what we're doing is we are eliminating exponentials by using logarithms. Just like the inverse to addition is subtraction, the inverse to multiplication is division, roots and powers. The way that we get rid of exponential numbers is by using log bases of the same amount. Log bases of the same amount, not the power, but the base. So the way we get rid of a base, you'll hear me say this, it's not technically right, but the way we get rid of a base is with a log base. So you can see these little examples that we have here. When a log base b meets a base b, those two values are going to eliminate, and all we will have is whatever was left in the exponent. We're not going to do logarithms today, but this process is going to work as well. The way we get rid tomorrow, the way we get rid of a log base is by using a base of the same amount. So essentially, they offset one another. A log base offsets a base. So that's how we will get rid of an exponential function. I don't think possibly that may be so clear, but the examples I think will clarify what I'm trying to say. So let's take a look at these 4. These are not on a Delta Math or a Canvas. These are just examples, but I would strongly suggest that you copy these down for your own record. So the first thing we're going to do is a very basic equation. So what we have here is a 5 to the n power is equal to 15. The way that we are going to get rid of a base 5 is by using a log base 5. So what happens is log base 5 cancels the base 5, and what we have is just the n value. Now, as always, what we do to one side, we have to do to the other. So this is going to be a log base, and the way that we know this to look is log base 5 on 15. And again, this is a number that we're looking at there. We just need to decide what number that is. So remember our process to getting to that. What we need to put into our calculator is, or type into the calculators, we have to hit alpha. And then we will hit the window button, which is F2 when you hit alpha. And then the 5th option is log base. So that's the series we'll go through as we do those. When I put log base 5 on 15, what I learn is my solution is, and we're doing to the 10,000ths place, so this would be 1.6826. We're going to have a lot of irrational numbers because we're doing log base, and this just frequently is how these will result. So you can see we have a few extra steps on this one. The first thing we need to recognize is before we can do anything, we have to isolate the base. So we need to isolate the 17 before we can ever get to the k, which is stuck in our exponent here. So anything that is on the same side as our base value that is not part of the base value has to be moved. So in this case, that would be the plus 2. So we add 2 to both sides, and what we end up with is 17 to the 5k power equals 74. Notice I left myself a nice little gap there. Reason why I left myself a gap is because I know what's about to happen. I'm about to take the log base of 17. So let's go ahead and do that. The way I get rid of a base 17 is with a log base 17. What I do to one side, I have to do to the other side. So log base 17 on base 17 cancels, and we just have 5k. On the other side, we are doing log base 17 on the number 74, and what we get is 1.5191. And if you really wanted to stay accurate as long as you possibly can, really the smart move would have just been to take this log base 17 on 74 and divide it by 5, because that's what we're about to do next. We're about to get the k by itself by dividing both sides by 5. Since I'm dividing from a number that I rounded, by the way, I need to note that it's rounded. Remember, the way we note a rounded value is with the approximation sign. So when I divide that number by 5, what I get is 0.3038, and then there's a 29, so the 2 is going to round up to 3. And that's actually one extra decimal place than I needed. And the last two are basically the most difficult ones we can come up with. They just have a lot of steps. Now, if you are doing this, it's actually going to behave just like if this equation were 6x minus 4 equals 32. So if you don't recognize what I've done here, I've replaced the base 19 with a variable. So if you get lost on these, think of it this way. If we were looking at this equation that I have written in yellow, the first thing we would do is we would add 4 to both sides in order to isolate the x. Well, we are following the same process. We're trying to isolate the base number, so the first step is to add 4 to both sides. So this would become 36. Now I'm going to tell you the most common mistake that's going to happen. Please don't be the one that makes this mistake. The mistake that we most frequently will see on these is a lot of people want to multiply that 6 times a 19. Do not make this mistake. Do not make this mistake. Somebody will, don't let it be you. The 16 is not actually multiplying by a 19 because the 19 is bigger than that. It has an exponent. So if I can't distribute the 6 or multiply the 6 times the 19, what I'm going to do is divide it away from both sides. So now it's going to be 19 x plus 5. 36 divided by 6 is 6. So we get to this point. We are needing to get rid of base 19. So we do that with log base 19. What we do to one side, we have to do to the other. So log base 19 on 19, that's really easy. Those values just cancel one another out. Log base 19 on 6 is another story. And again, if I wanted to leave this accurate, I could just leave it this way. Actually, we'll do it this time. So we have x plus 5 equals log base 19 on 6. And then I'm going to subtract the 5 over. I'm going to subtract the 5 over. Tack that onto the back. Remember, do not subtract the 6 minus. That's why I would probably suggest several of you not doing it this way, because it's not 6 minus 5. 6 is part of a very big operation that's going on here, but in the end we're going to subtract 5 from both sides. So I'm going to subtract 5, and what I learn is that x is equal to I rounded. I'm about to round, so if I'm about to round, I got to remember to show everybody that I'm rounding. So it ends up being negative 4.3991, and then it's 4.7, so the 4 is going to round up to a 5, and then we have this answer. Now, if we were asked to write the answer in exact form, we were asked to write this in exact form, we would take this value that we see right there. So the exact answer to this would be log base 19 on 6 minus 5. 6 could be in parentheses. That's the exact answer, but we are right now doing decimal answers, so we're good with negative 4.3915. And the last example. Our last example deals with Euler's number. People oftentimes fret about these, but really once you understand what it is, it's really one of the easier questions. So in this case, the one thing that I usually see students struggle with is they want to conceive E as a variable, but E is a number. E is the number 2.7183 or something in that ballpark, but E is not a variable. It acts like it sometimes, but it is not a variable. So in this case, we still have to follow that rule of isolating the base. Well, the base in this case is E. So we need to isolate the E. We're going to take care of the plus 1 first to move that away. So once we do that, we have 8e to the 5p power equals 90. So it's 8 times e. So we divide both sides by 8. And again, we're going to leave this in fraction form for the current moment. Let's do a rewrite, see what we have here. We have Euler's number to the 5p power equals 90 over 8. So the reason why I'm leaving it this way, it's 11 1/4, but I know what my next step is. And the way we get rid of Euler's number is with our good friend natural log. So I go natural log to both sides. When natural log meets Euler's number, they cancel, and we have the 5p amount. Now, natural log has its own button. Remember, it's right beside the number 4. So I'm going to put that in my calculator. Natural log of 90 over 8 is approximately 2.420 then the 3 rounds up to a 4. And then the last thing we do is we divide both sides by 5. And we learn, we'll write this over to the side, P equals approximately 0.4841. If we were asked to write this in exact form, what we would do is we would have left that natural log of 9/8, and then we could have divided by 5 or multiplied times 1/5. To be honest, this is more likely, if we were looking for an exact answer, the exact answer you would see. Today we're working with decimals though, so we are going to take this decimal answer right here and go with it. All right, you guys have a Canvas assignment on this one. Good luck.